Welcome to this course about FastAPI, Part 1. Here's what we'll cover step by step in this notebook. Chapter 1, Getting Started. Learn what FastAPI is, why to use it, install it, create your first API, explore routes, and interactive docs. Chapter 2, Requests and Responses. Handle path and query parameters. Request bodies with Pydantic, and send JSON responses with status codes. Chapter 3, Data Validation. Use advanced Pydantic models, structured response models, and handle errors with custom messages. Chapter 4, Databases connect to SQL databases with SQL Alchemy. Understand sync versus async calls, perform CRUD operations, and use Alembic for migrations. Chapter 5, Authentication. Secure your API with username and password, OAuth 2 with JWT tokens, and role-based access control. Chapter 1, Getting Started with FastAPI. What is FastAPI? FastAPI is a modern web framework for Python. It is designed for building application programming interfaces, or APIs, quickly and efficiently. Unlike older frameworks such as Flask or Django, FastAPI is built on ASGI, which stands for Asynchronous Server Gateway Interface. This makes it very fast and capable of handling many requests at the same time. One of the key strengths of FastAPI is that it is both beginner-friendly and professional-ready. You can start small, but the framework can also scale for large production systems. FastAPI uses a library called Pydantic for data validation. This means when you receive input from a client, such as JSON data, FastAPI automatically checks if it matches the expected structure and types. You don't have to write extra validation code. Another powerful feature is automatic interactive documentation. As soon as you define your API endpoints, FastAPI generates documentation pages. These pages let developers see all available routes, understand request and response models, and even test the API directly from the browser. So, in short, FastAPI is modern, fast, and makes development easier by combining speed, validation, and documentation right out of the box. Why should we use FastAPI instead of another framework? The first reason is performance. FastAPI is one of the fastest Python frameworks available today. Its performance is comparable to Node.js and even the Go language. This is possible because FastAPI is built on ASGI and uses modern asynchronous programming. The second reason is asynchronous support. With async and await, your application can handle thousands of requests efficiently. Especially important when your API talks to databases, external services, or other APIs. Instead of blocking and waiting, FastAPI can continue processing other requests. Another major benefit is automatic validation. By using Python type hints together with Pydantic, FastAPI automatically checks incoming data. For example, if a user sends a wrong data type, FastAPI will return a clear error response without you writing extra code. Next is interactive documentation. This feature comes built in. As soon as you create endpoints, FastAPI provides a Swagger UI page and a redoc page. These let you test APIs directly in the browser. Developers love this because it saves time and makes collaboration easier. Finally, ease of use. FastAPI requires very little boilerplate code. You can write a complete API with just a few lines. It is beginner-friendly, but at the same time, it is powerful enough for professional production systems. Companies like Microsoft, Uber, and Netflix already use it. In summary, FastAPI gives you speed, reliability, simplicity, and great developer experience. That is why it has become one of the most popular Python frameworks in recent years. Where to use FastAPI? Now that we know what FastAPI is and why it is powerful, the next question is, where should we use it? FastAPI is mainly designed for building APIs. This makes it perfect for REST APIs that power websites and mobile applications. For example, if you are building a mobile app that needs to talk to a server, FastAPI can provide the back-end service. It is also excellent for microservices architectures. In modern systems, applications are often split into small independent services that communicate with each other. Because FastAPI is lightweight, fast, and easy to deploy, it is well suited for building microservices. Another area is data processing and machine learning model serving. Many data scientists use Python, and FastAPI makes it simple to wrap a trained model inside an API. This way, other systems can send requests and get predictions in real time. FastAPI also supports real-time applications when combined with WebSockets. This means you can create features like live chat, notifications, or video streaming backends. It is also useful for Internet of Things or IoT devices. For example, sensors can send data to a FastAPI backend, which then processes and stores it. And finally, FastAPI works well for both prototypes and production systems. You can start small by quickly building a proof of concept and later scale it to a full production service without rewriting the code. So, whether you are building apps, microservices, AI solutions, or real-time systems, FastAPI is a strong choice. Install FastAPI and Uvicorn. To start using FastAPI, we need to install two things: the framework itself and a server to run it. First, we install FastAPI by running pip install FastAPI. This installs the FastAPI framework, which gives us the tools to build our API. Next, we need a server. FastAPI is built on ASGI, and the most commonly used server is Uvicorn. We install it with pip install Uvicorn. Now we can run our first application. Suppose our application code is saved in a file called main.py. We can start the server with uvicorn main:app-reload. Here, main refers to the Python file name without the .py extension. App refers to the FastAPI instance inside that file. The option reload tells Uvicorn to automatically restart the server whenever you change the code. This is very useful during development. Now let's create our very first FastAPI application. The process is simple. Step 1. Import FastAPI from the FastAPI module. Step 2. Create an instance of FastAPI. This instance will be the core of our application. Step 3. Define a route using a decorator. In this case, we use @app.get/quote to tell FastAPI that this function should respond to a GET request at the root path. Inside the function, we return a dictionary with the message, "Hello World." FastAPI automatically converts this dictionary into JSON when sending the response. Finally, we run the application with Uvicorn, just like before. To run the application, type in the terminal uvicorn main.py:/app-reload. When this is executed, you can open the browser and visit http://127.0.1:8000. You will see a JSON response that says, message equals hello world. Understanding routes basics. In FastAPI, a route defines how your application responds to different requests. Routes are linked to URL paths. For example, /hello is one route. We use decorators to define routes. The most common ones are @app.get and @app.post. The get method is used to read data. For example, fetching information from the server. The post method is used to create data, such as sending a new record to the server. In this example, when a client sends a GET request to /hello, the server returns a message saying hello from GET. When a client sends a POST request to /hello, the server returns a message saying hello created with POST. We create a FastAPI app instance once and use it to register routes. The decorator at app.get with path /hello registers a GET endpoint. The function returns a Python dictionary. FastAPI converts it to JSON automatically. Set status code 200 and content type application/JSON. The decorator at app.post with the same path registers a separate post endpoint. Even though the path is the same, the methods are different, so FastAPI treats them as two distinct endpoints. Function names are for readability. FastAPI uses the path and method, not the function name, to route the request. Understanding routes. More methods. Besides GET and POST, there are other HTTP methods that we commonly use. PUT is used to update existing data. For example, editing a record in the database. Delete is used to remove data from the server. Just like before, FastAPI provides decorators. You can use @app.put for put requests and @app.delete for delete requests. In this example, sending a put request to /hello returns the message hello updated with put. Sending a delete request to /hello returns the message hello deleted with delete. These four, get, post, put, and delete, are the most common HTTP methods used when building REST APIs. FastAPI automatically generates interactive documentation. When you start your application, you can visit /docs. This opens Swagger UI. It shows all your routes grouped by method and path. Developers can expand each route, see what inputs are required, and try requests directly in the browser. This saves time when testing and helps teams collaborate, since no manual documentation is needed. In this example, we define one GET route at /hello. After running the server, FastAPI makes it visible in Swagger UI automatically. Opening /docs shows this endpoint. The docs page is interactive, meaning you can click Try it out, execute the request, and see the JSON response directly in the browser. No extra configuration is required. FastAPI generates this page for every route you create. Besides Swagger UI, FastAPI also generates redoc documentation at /redoc. Redoc provides a clean, professional layout. It is read-only, so you cannot test requests directly. However, it is very useful as an API reference. Teams often share redoc with external developers because it is easy to navigate and read. The same FastAPI application that produced Swagger UI at /docs also produces redoc at /redoc. FastAPI automatically builds both. Redoc lists endpoints, request and response schemas, and details about query parameters. It is designed to be human-friendly documentation for developers who need to understand your API structure. Chapter 2: Request and Response Basics. Path Parameters Basics. Path parameters let us capture values directly from the URL. We define them inside curly braces in the route path. The function receives the value as an argument, and the argument name must match the name in the path. This allows us to build dynamic routes. For example, /items/10 will return the item with ID 10. In this example, we define a GET route with the path /items/curly braces item_ID. This tells FastAPI that the last part of the path is a parameter. The function read_item has a parameter named item_ID, which matches the name in the path. When a request is sent to /items/123, FastAPI extracts the number 123 and passes it into the function. The function returns a dictionary, which FastAPI converts to JSON. Path parameters, type validation. FastAPI uses Python type hints for validation. If we declare the path parameter as an integer, FastAPI will automatically check that the input is valid. If the user tries /item/hello, FastAPI returns an error response since hello is not a valid integer. This makes our API safer and reduces the need for manual validation code. In this version, the function parameter item_id is annotated with type int. When a request is made, FastAPI converts the value from the path into an integer. If the conversion fails, FastAPI returns a 422 unprocessable entity error. Query parameters, basics. Query parameters are values added to the URL after a question mark. They are written as key equals value. For example, /items Q equals book. In FastAPI, you simply declare a function parameter, and FastAPI matches it to the query parameter automatically. This makes query parameters very useful for searching, filtering, and customizing results. Here we define a get route at /items. The function read_items takes a parameter q of type string. When the request is /items Q equals book. FastAPI passes the string book to the function. The function then returns a dictionary with the key query and the value book. If the request is /items Q equals phone, the response will contain query equals phone. Query parameters, optional and typed. Query parameters can also be optional. If we give a default value such as none, the user does not have to provide the parameter. FastAPI still handles the validation based on the type hints. This allows you to provide both flexible and strict API endpoints. For example, we import optional from the typing module. In the function, the parameter q is declared as an optional string with default value none. If the client sends /items Q equals book, FastAPI provides the value book. If the client sends /items without any query, FastAPI passes none. Inside the function, we check if Q has a value. If yes, return it in the response. If not, return the message no query provided. This is a common pattern for optional filters in APIs. Sending structured request body with Pydantic. When working with APIs, clients often need to send structured data in the request body. FastAPI uses Pydantic models for this. You create a class that inherits from base model and define the expected fields with their types. When a request is received, FastAPI automatically converts the JSON body into a Python object and validates the types. If the data does not match, FastAPI returns a clear error response. In this example, we import base model from the Pydantic library. We create a class called item, which inherits from base model. It has two fields, name of type string and price of type float. Next, we define a post route at /items. The function create_item takes a parameter item of type item. FastAPI automatically reads the request body, converts it into an item object, and passes it into the function. The function then returns the name and price as JSON. If the client sends invalid data, such as a string instead of a float for price, FastAPI will reject the request with status code 422. Validation and default values with Pydantic. Pydantic models do more than just define fields. They also validate inputs and support default values. If a required field is missing, FastAPI automatically returns an error response. If a field has a default value, it becomes optional, and FastAPI will use the default if the client does not provide it. This makes APIs both strict and flexible at the same time. In this version of the item model, we add a new field called description of type string. We assign it a default value of no description. Now, if the client provides name and price but not description, FastAPI will still accept the request and set description to no description. If the client provides all three fields, FastAPI will use the provided values. If the client omits a required field, such as price, FastAPI automatically rejects the request with status code 422 and includes details in the JSON error response. JSON responses and status codes. FastAPI returns JSON responses by default. Whenever you return a Python dictionary, FastAPI automatically converts it into JSON for the client. The default status code is 200, which means request successful. You can change the status code using the status_code parameter in the route decorator. For example, when creating a new item, it is common to return status code 201, which means created. Using proper status codes makes your API predictable and easier to integrate with other systems. We import status from FastAPI to use predefined constants. The first route at /success is a GET endpoint. It returns a dictionary with the message request OK. FastAPI converts it to JSON and assigns status code 200 by default. The second route is a post endpoint at /created. Here we add the parameter status_code equals status.http_201_created. This sets the response status code to 201 instead of 200. When a client calls this route, the JSON response will include message equals item created with status 201. Chapter 3: Data Validation and Serialization. Advanced Pydantic Models. Pydantic models make your API data safe and reliable. Every field has a type, so FastAPI validates requests automatically. If a client sends the wrong type, the framework rejects it and returns a clear error. You can also add default values. For example, the field in _stock defaults to true. That means clients do not need to send it every time. If you want a field to be optional, you declare it with optional from the typing module. For example, description can be a string or left out entirely. This way, you define exactly what data is required and what data is flexible. It prevents bad data from reaching your business logic. We define an item model with 4 fields. Name is a required string, and price is a required float. In_stock is a Boolean field with default value true. If the client omits this field, FastAPI assigns it automatically. Description is declared as optional string with default value none. This means the client can either provide a string or skip the field. When a client sends a post request with a valid JSON body, FastAPI parses it into an item object and returns it as JSON. If the client sends the wrong type, such as price as a string, FastAPI rejects the request with status code 422 and includes a detailed error message. Response models for structured output. Response models give us control over what information is returned to the client. We often store more data than we want to expose, such as passwords or internal IDs. By using the response model parameter, we can filter out sensitive fields automatically. This keeps responses consistent, makes our API safer, and improves documentation clarity. Here we define 2 models. The user model includes username, email, and password. The user out model includes only username and email. In the route, we accept the full user model as input, but we set the response model to user out. That means FastAPI automatically removes the password when sending back the response. If a client sends a request with all 3 fields, the output will include only username and email. This prevents sensitive information from leaking to the client. Handling errors and custom error responses. FastAPI automatically checks incoming data and returns errors if something is invalid. For example, When a required field is missing or has the wrong type, FastAPI responds with status code 422. In real applications, we also need to raise our own errors. We can do this using the HTTP exception class. This lets us control the status code and the message. Custom errors help us communicate clearly with the client, making it obvious what went wrong and how to fix it. In this example, we simulate a simple database with 2 items. When a client requests an item by ID, we first check if the ID exists. If the item is not found, we raise an HTTP exception with status code 404 and a message saying, "Item not found." FastAPI then returns this as a JSON response. If the item exists, we return its ID and name. This pattern makes it easy to handle errors in a clean and predictable way. Chapter 4: Working with Databases. Connecting FastAPI with SQL databases, SQL Alchemy. FastAPI works very well with SQL databases by using SQL Alchemy. SQL Alchemy is an object relational mapper, also called ORM. It allows us to define database tables as Python classes. To connect, we first create an engine that points to our database. Then we use a session object to query or save data. This approach keeps our code clean and structured, while still using the full power of SQL databases. In this code, we set up a database connection using SQL Alchemy step by step. First, we define the database URL. The database URL tells SQL Alchemy to use SQL Alchemy as the database engine and to store the database file in the current folder with the name test.db. Next, we call createEngine, which builds the actual connection to the database. We pass in the database URL and also an option called checkSameThread equals false. This option is specific to SQL Alchemy. It allows the database to be accessed safely from different parts of our application. After that, we create a session factory using SessionMaker. The session is the object we use to talk to the database. We pass 3 important parameters. Auto-commit is set to false, meaning changes are not saved automatically. We control when to commit. Auto-flush is set to false, meaning SQL Alchemy does not push pending changes to the database until we tell it to. Bind equals engine, which means this session will use the database engine we created. Then, we define a base class using declarative base. This is the starting point for all of our database models. Using this base, we define a user class that represents a database table. The table is called users. It has 2 columns, ID, which is an integer primary key, and name, which is a string. When we call base.metadata.createAll, SQL Alchemy automatically creates the users table in the database if it does not already exist. Finally, in the FastAPI route /users, we create a new session from session local, query all users in the table, and return them as JSON. This flow, defining the engine, creating sessions, and declaring models, is the standard pattern when working with SQL Alchemy in FastAPI. Async versus sync DB calls. In web development, how you interact with the database is critical for performance. Synchronous database calls block the server until the query finishes. That means if one request is waiting for a slow query, other requests may also get delayed. Asynchronous database calls, on the other hand, do not block. While waiting for a query to finish, FastAPI can continue serving other clients. This makes async the preferred choice for applications that expect high concurrency or lots of simultaneous users. FastAPI supports both sync and async database access. SQL Alchemy also has support for both modes. Sync is easier for simple scripts or small projects, while async is better for large production systems where scalability matters. Let's start with the synchronous example. We use Create Engine to make a normal SQL Alchemy engine that connects to a SQLite database file. The endpoint /sync users opens a database connection inside a with block, executes a simple select statement, and returns the result as JSON. Because this is synchronous, while this query runs, the FastAPI server cannot handle other requests. The request thread is locked until the database responds. Now let's look at the asynchronous example. Here we use Create Async Engine instead of Create Engine. This sets up an engine that speaks to the database using asynchronous drivers like AIO SQLite. We also define async session local using async session maker. This factory function creates async session objects, which are special sessions that can be awaited. Inside the async user's endpoint, we open a session using async with. This ensures the session is cleaned up properly when the request is finished. The query execution is written as await session.execute. Because of the await, FastAPI does not block the server. While the database is responding, the server can continue processing other incoming requests. Finally, notice how results are handled differently. In async mode, we use result.mappings.all. The mappings call returns rows as dictionary-like objects instead of raw tuples, making them easier to convert to JSON. To summarize, synchronous database calls are easier to understand, but block the server while waiting. Asynchronous database calls are a bit more complex to set up, but they allow FastAPI to handle many users at once without being blocked by slow queries. That's why async is usually the better option for production systems with high concurrency. CRUD operations. CRUD stands for Create, Read, Update, and Delete. These are the 4 basic operations used to manage data in a database. In FastAPI, we usually handle CRUD operations using SQL Alchemy ORM. Each operation is exposed through an API route, so clients can create new records, read existing ones, update them, or delete them. For example, a client may send a POST request to create a new user, a GET request to fetch users, a PUT request to update user data, or a delete request to remove a user. This pattern is extremely common in real-world applications because nearly every backend system works around CRUD functionality. This code shows a complete example of CRUD operations in FastAPI using SQL Alchemy. We start by setting up the database connection. The database URL points to a file named test.db. We create an engine with Create Engine, and then set up a session local factory with Session Maker. This factory is used to open database sessions for each request. We also define a base class with declarative base, and from it, we define our user model. The user table has 2 fields, ID as the primary key and name as a string. Next, we add a getDB function that acts as a dependency. This ensures that each request gets its own session, and the session is closed properly when the request ends. Now let's look at the CRUD routes. Create. The endpoint /users accepts a name as input. We create a new user object, add it to the session, commit the transaction, and return the user with its assigned ID. Next is read. The endpoint user's user ID fetches a user by ID using db.get. If the user does not exist, we raise an HTTP 404 error. Otherwise, we return the user object as JSON. Next is update. The endpoint user's user ID with the put method lets us update a user's name. We first fetch the user. If it exists, we update the name, commit the change, and return the updated record. If it does not exist, we return a 404 error. And finally, delete. the endpoint users/user ID with the delete method removes a user from the database. If the user is not found, we raise a 404. If found, we delete it and commit the change, returning a confirmation message. Using Alembic for database migrations. Alembic is a tool that works with SQL Alchemy to handle database migrations. A migration means changing the database schema, like adding a column or creating a new table, without losing existing data. This is important when your application grows and the database needs to evolve. Instead of manually updating tables, Alembic creates migration scripts. These scripts record changes step by step, so the database can be upgraded or downgraded reliably. The workflow is simple. First, you initialize Alembic in your project. Then, whenever you update your models, you create a new revision. Alembic generates a migration file. Finally, you apply that file to the database with the upgrade command. In short, Alembic keeps your database schema and your SQL Alchemy models perfectly in sync, which is critical for production systems. First, we install Alembic using pip. The command alembic init alembic creates a folder called alembic with configuration files. This is the starting point for migrations. Next, whenever we change our SQL Alchemy models, we run the command alembic revision --autogenerate with a message. In this example, the message is create users table. Alembic scans our models and generates a migration file with the differences. To apply the migration, we use Alembic upgrade head. This updates the database to the latest version. If we ever need to roll back, we can use Alembic downgrade -1 to undo the last migration. This workflow ensures that our database evolves in a safe and controlled way. Chapter 5: Authentication and Authorization. Basic authentication, username, password. Basic authentication is the simplest way to protect routes in FastAPI. With this approach, a client must send a username and password with every request. FastAPI provides a security class for handling HTTP basic authentication. When a protected endpoint is called, FastAPI automatically checks the provided credentials. If they're missing or wrong, it returns an unauthorized error. This is fine for demos or internal tools, but it's not recommended for production. Passwords are sent in plain text unless HTTPS is used, and there's no session management. For real-world systems, OAuth 2 with JWT tokens is the more secure choice, which we'll cover next. Here we define a FastAPI app with HTTP basic authentication. We first import the HTTP basic class from FastAPI's security module. This handles the process of extracting credentials from the request. We define dummy credentials. The username is admin, and the password is secret. The root/secure data depends on the security object. This means FastAPI will automatically look for a username and password in the request. Inside the function, we check if the credentials match our dummy values. If not, we raise an HTTP exception with status code 401, which means unauthorized. If the credentials are correct, the API returns a JSON response with a welcome message. This demonstrates the basics of authentication, but for real systems, you'd validate credentials against a database and move to stronger methods like OAuth 2. Let's walk through the setup for JWT-based authentication in FastAPI, step by step. We begin with imports. From typing, we import any and dict, which help us annotate our functions with precise types. From datetime, we bring in datetime and time delta, which we will use later to set token expiration times. Next, we import the core FastAPI components, FastAPI itself to create the application, depends for dependency injection, HTTP exception for structured error handling, and status, which gives us predefined HTTP status codes like 401, unauthorized. From FastAPI.security, we import OAuth2 password bearer and OAuth2 password request form. These are specialized helpers that FastAPI provides for OAuth2 authentication. The password form helps us handle login requests, where a user submits a username and password, while OAuth2 password bearer automatically extracts and validates the bearer token from the request headers. From JOES, we import JWT error and JWT. The JOES library is a well-known Python package for working with JSON web tokens. JWT error will allow us to catch and handle decoding errors, and JWT is the utility we use to actually encode and decode tokens. Next, we create the FastAPI app instance as usual. After that, we configure our authentication system. We define a secret key, which is used to sign and verify tokens. In a real-world application, this secret key should not be hard-coded. It must be stored securely in environment variables or a secret manager. For our demo, we keep it simple. We also specify the algorithm, in this case, HS256, which is HMAC, using SHA-256. This is the most common algorithm for signing JWTs. We define an expiration time of 30 minutes. This means that any issued token will become invalid after 30 minutes, forcing users to re-authenticate. Short expiration times improve security. Next, we configure the OAuth2 password bearer scheme. This is a FastAPI helper that automatically expects a token in the authorization header of incoming requests in the format bearer space token. The parameter token URL points to the endpoint where clients will obtain tokens. In this example, that will be /token, which we will implement later. Finally, we define a fake user for demonstration. In real applications, you would look up users in a database. For now, we hard-code a dictionary with a username, Alice, and a password, Wonderland, to keep the flow simple. This completes the setup. At this stage, we have our app configured, our security scheme defined, and a demo user ready. In the next step, we will add the function that actually generates access tokens. Here we define the function createAccessToken, which generates a new JSON web token for a user. The function takes two parameters: data, which is a dictionary of claims. Claims are pieces of information that you want to embed inside the token, such as the username.expires_delta, which is an optional time delta. If provided, it sets the lifetime of the token. If not, we default to 15 minutes. Inside the function, we first make a copy of the data dictionary. This ensures we don't accidentally modify the original input. Next, we calculate the expiration time. We take the current UTC time, add either the given expires delta or a default of 15 minutes, and store that in the variable expire. We then update the dictionary we're encoding with a special field, exp. This is a standard JWT claim that defines when the token should expire. Token consumers, like FastAPI, will automatically reject tokens that have passed this expiration time. Finally, we call jwt.encode to actually create the token. We pass three things: the dictionary of claims, which now includes both our original data and the expiration; the secret key, which ensures that only the server can sign tokens and later verify them; the algorithm, HS256 in this case, which defines how the signing is done. The function then returns the encoded JWT as a string. This token will later be sent to the client and included in their requests to prove their identity. This helper function is central to our authentication system because it encapsulates the logic for creating secure, time-limited tokens. Here we define the login endpoint add token. This is the part of the system responsible for authenticating the user and issuing a JWT token if the credentials are correct. The function accepts form data, which FastAPI automatically extracts using OAuth2 password request form. This form contains two fields, username and password, which are typically sent from a login form or an API client like Postman. Inside the function, we first validate the credentials. We check whether the provided username and password match the values in our demo fake user dictionary. In a real-world application, this check would involve looking up the user in a database and verifying a hashed password. If the credentials don't match, we raise an HTTP exception with status code 401. This means unauthorized, and the client knows that the login attempt failed. If the credentials are correct, we create an expiration time for the token. Here we use our earlier configuration constant, access token expire minutes. We then call the helper function createAccessToken, passing in a dictionary that contains sub, form data, username. The sub claim stands for subject, and in this case, it's the username of the authenticated user. We also pass the expiration time so the token will be valid only for a limited period. Finally, we return a JSON response containing two fields. Access token is the JWT string that the client should store. Token type is set to bearer, which tells the client how to use the token in future requests. From this point forward, the client can include the token in the authorization header when calling protected routes. FastAPI will then verify the token to check identity and permissions. This is our protected endpoint. Only requests with a valid JWT token can reach it successfully. In the function readProtected has a dependency called OAuth2Scheme. This automatically extracts the token from the request's authorization header, where the client must send it as bearer token. Inside the function, we attempt to decode the token using jwt.decode. We provide three arguments: the token string itself, our secret key, which was used to sign the token, and the expected algorithm, in this case HS256. If the token is invalid, for example, if it's expired, signed with the wrong key, or tampered with, the jwt.decode call raises a JWT error. In that case, we catch the exception and return a 401 unauthorized response. Next, we pull the sub claim from the decoded payload. Recall that sub is the subject, which in our system is the username. To avoid type errors and strengthen validation, we explicitly check that the value is a non-empty string. If it's missing or malformed, we raise another HTTP exception with status 401. If everything is valid, we assign the username and return a simple JSON response saying, "Hello username, you are authorized." This demonstrates the full flow. A client logs in at token to receive a JWT. The client attaches that JWT as a bearer token in the authorization header. FastAPI extracts and validates the token before granting access to protected endpoints. This pattern is the foundation of secure login systems, and you can extend it with additional claims, expiration checks, or role-based access control. Role-based access control, or RBAC, assigns roles to users, such as user, editor, or admin. A role is a named permission set that defines what actions a user can perform. Roles can be embedded inside a JSON web token when the token is created, or they can be looked up from the database on each request. On every protected endpoint, a dependency or middleware extracts the roles for the current user and checks them against the required role for that endpoint. If the user does not have the required role, the API returns status code 403, forbidden. Use the least privilege principle. Give users only the roles they need. Keep role names simple and stable, and make changes auditable so you can track who received or lost permissions. For critical permission changes, consider server-side checks or short token lifetimes to avoid stale tokens in long-lived tokens. Now that we have authentication working with JWT tokens, let's add role-based access control. First, notice we updated our fake user record. In addition to username and password, this user now has a roles field containing both user and admin. In a real application, these roles would come from a database query when the token is created. Next, we define a new dependency called getCurrentUserRoles. This function decodes the token just like before, but instead of reading sub, it extracts the roles claim. We make sure that the roles value is a list. If it isn't, or if the token is invalid, we raise the appropriate HTTP exception. Finally, we create a protected endpoint at /admin. This endpoint depends on getCurrentUserRoles. Inside the function, we check if admin is in the roles list. If not, we return a 403 forbidden error. Otherwise, we return a success message that says, "Welcome admin, you have full access." This pattern allows you to enforce different levels of access in your API. For example, /profile could be accessible to any authenticated user. Admin could be restricted to only those with the admin role. You could even add finer-grained roles like editor or moderator. By combining JWT tokens with RBAC, you get a secure and flexible way to control what each user is allowed to do. Thanks for watching.